140, 160. This is L over R. Okay, and we have determined 88.86. Okay, so I'm going to sketch out our 88.86 line. So this is where we have our 88.86. So 88.86. So this is just eyeballing. Okay, so this is the line, and this line represents 88.86. So we again have a laudable of 250. So 250 times 10 to the power 6. Okay. So at 88.86, what does it actually mean? Okay. So when it's from 0, okay, so we have 0 over here to 88.86, I'm going to sketch a horizontal line. Okay, I'm going to sketch a horizontal line. Then beyond 88.86, okay, we are going to have a slope coming down. So what does this mean? Okay, what does this mean? If your L over R ratio is greater, so if it's greater than, so over here, L over R ratio is greater than 88.86, okay? You must consider buckling analysis, okay? And when the L over R ratio is greater than 88.86, for example, now it is at 120, right? For example, now, what you realize that the stress at this point, the stress allowable is less than what? 250 times 10 to the power 6. How much? We don't know. We know it's less, okay? So the trend down here, okay, the trend down here is determined empirically. Okay, empirical. Okay, empirically means it's done by doing what? Experimental work. Okay, we only know that it's not going to be what? 250 times 10 to the power 6. Okay, we know that it's going to be less than that. How to know that value? We have to determine experimentally. And there's a material handbook that I will show you that has this value. Now, if L over R, right, is less, okay, or is less than 88.86, like for this case, in this region on the left-hand side, our design criteria will be based on stress allowable is equal to P over A, or deflection is equal to PL over AE. Okay, you can use the standard formulas, so-called the standard formulas. If it's greater than 88.86, you have to consider what? Buckling. Are we clear? Okay, so I remember Lee was asking me, what is this L over R ratio? Okay, or when do you actually need to analyze or determine, or when do you actually need to analyze based on buckling? It's based on the what? L over R ratio. And 88.86 is determined by what? It's determined by, it's controlled by two things. Pi is constant, is controlled by the Young's modulus and the what? Critical stress. Okay. So this is how we use, okay, this is how we use these values. Okay. Later on in the example, I'll show you how can we design structure that is safe for buckling. Okay. Now, the next thing that we are going I'm going to teach you. Anyone before I go on, anyone any question that you have to ask? Anyone? I don't see anyone have a critical question, so I'll carry on. Yes. No. If there is, you can ask. Okay, there's no question. Okay, so the next thing we are going to talk about is we are going to look into, let me see. Okay, let's do one example now. Okay, because I want you to look at how to calculate the second moment of area. Okay, so I'm going to do this example now. So this is, you can find this on Avenue to Learn. Okay, so I'm gonna copy this. Let's look at an example, then we go into more theory, or not like last week, too much theory. You guys feel really bored. And then okay. So this is our example number 2. We have a column that has a effective length of 6 meters. It's made of 3 plates as shown. Okay, so these 3 plates are joined together. Using the Young's modulus as 200 gigapascal, determine the factor of safety with respect of buckling for a centric load of 16 kilogram. Okay. So what we are given is the effective length. Later on, when I teach the extended theory of Euler's equation for buckling, we'll talk more about this effective length. Okay. So for now, we are given that the effective length L is equal to 6 meters. Okay, and this is the cross section of our structure. And if this is a cross section, what I'm going to do is I'm going to label this. I'm going to draw my transformation. Okay, so I'll draw the normal transformation that is commonly used. Okay, so this is my y, and this is my z. Okay, so this is the most commonly used configuration. Later on, when we do more example, you see why. So what is given to us is we know that we have a Young's modulus that is equal to 200 times 10 to the power of 9 Pascal. And we know that we have a centric load. Okay, so this load is going to come in the x-axis. Okay, so px is coming in at minus 16 times 10 to the power 3 Newton. Why I put minus? Because buckling will only occur when the force is applied in compression. Okay, so we know px is equal to minus 16 times 10 to the power 3. So what we are going to calculate is we're going to calculate a factor of safety. Okay, we're going to calculate our factor of safety, which is equal to P critical over Px. Okay. So we have written quite a few formulas already. Okay. So we also know that Px, or we also know that how to calculate P critical, right, is equal to pi squared over L squared, right, E and I. Now, this structure can deform in two axes. Okay, let me extend let me draw this structure. Okay, in 3D now. Okay, so now this is how our structure look like now. Okay, so our structure have one like this, and then has another line of this, and then I'm going to join this. Okay, and then we have vertical. And then we have two, 1, 2, 4, 6, 8, 9, 2, 4, 6, 8. Okay, this is our structure. So the way we label our transformation, we know that this direction is our Z. We know this direction is our Y, and we know this direction is our X. Okay. So we are aware that we have a load applied at a centroid, okay, directly on the centroid. Yeah, I did not draw this well. So directly at the centroid over here. And this is applied at 16 times 10 to the power 3 Newton. Okay. So this structure can buckle in two ways. Okay, this structure can buckle in two ways. The first one, if we just consider the XZ plane. Okay, so now I'm going to sketch on the XZ plane. So this is our plane. And with our XZ plane. Okay, so I'm going to now sketch our transformation now. So this is my X, this is my Z, and this will be my rotation in the Y. Okay, so when I sketch this out, this is how the structure will look like. So 2, 4. Okay, and you have the dotted point over here, which is the web. So this is one way that the structure will buckle. Okay, so the confusing thing is this. Okay, if this thing were to deform, okay, for example, if this thing were to deform, it will deform in this direction. Okay, so I'm going to draw just the center part, how it will deform due to buckling. Okay, it's going to deform in this way. So this is the deformation. And the deformation is about the what? The y-axis, or so-called this rotation over here, right? You can see so-called like